and I finished the Master's Sustainable Cities in Copenhagen just last summer. So what I'm going to present is actually the thesis that I made, and on the same topic, Nis and actually also Peter Carney, which is one of the professors in Copenhagen, are now doing a paper about the same topic. So that's what I'm going to present. The topic is thermal energy storage in Greater Copenhagen, and it's quite an interesting story, because there's this new thermal storage that they want to build, but they don't know how to split the investment in between different stakeholders. So that's what we try to work with, and what I'm going to talk a bit about. Yeah, so the agenda is the context, the problem, our approach, our findings, and briefly about what's the status of the project right now, and our ideas for the paper. In general, thermal energy storage has the potential to decouple heat production from heat demand, so that CHP plants typically can produce electricity and heat when there is a high electricity price, for example, and without having to think about that they need to deliver that heat to some heat consumers. They can just put that heat into the thermal energy storage. But just to clarify, I don't know how much you know about thermal energy storage, but just heat storage is for district heating. So the thermal energy storage, having this quality of decoupling the two, they have the ability to increase CHP production. They have the ability to reduce boiler production, which is generally a good thing, and CHP plants will typically be able to generate more income on the electricity market, because they can produce more flexibly depending on the electricity price. So this is the sort of the typical benefits. But in the district heating system of Copenhagen, it gets more complicated, because there's not just one player who invests in the storage and owns and operates it how he wants to. There are a lot of different actors and different plants, and when you put one storage into the collective system, it gets complicated. So we have the district heating system of Copenhagen on this map, and it goes to show that there are a lot of players involved. We have two transmission companies who transmit the heat across the whole area of Copenhagen. We have VEX, which supplies the blue area, the west, and we have CTR, which is another company who supplies the north and east part of Copenhagen. And then we have several municipal district heating companies, which distribute the heat in all the individual municipalities. And furthermore, we have several plants. We have three waste incineration plants, which are these blue ones there. And we have four CHP plants, which are the greenest one here. This is actually one, just 2 units, and then this one. And to top that off, we have currently have 2 large-scale storages also. One at Løværket and one at Arnaværket. So the story of the new thermal energy storage that was supposed to build started with a project called Heat Plant Copenhagen. There was a big modeling effort to figure out what we wanted to do with, or what the stakeholders of the district heating system wanted to do for the future development of the system. And this project concluded that the district heating system of Copenhagen would benefit from increasing the thermal energy storage capacity. They could see that most likely the CHP plants would produce more and it would use less natural gas on the boilers. But the project didn't come to where the storage should be placed, or what type of storage, or who should pay for the storage. The current existing two storages were just based on a very simple division between the two big transmission companies and Elvera, which just paid 1/3 each, and the other one up in Ama, the two transmission companies and Ama paid 1/3 each. But for increasing the storage capacity, they didn't want to follow the same investment strategy, because they could see that all of the waste incineration plants and the other CHP plants would also benefit from it. So they didn't know who should pay what. And then it happened that Høje Taastrup District Heating Company, which is just a local district heating company, Høje Taastrup, they proposed building a great pit thermal energy storage in their area. They had a cheap open field, and they had the area close to the transmission cables and also close to the distribution of Høje Taastrup. And to top that off, they had a heat pump which produces a lot of cooling in the summer, and during that time when there's low heat demand, they were thinking of putting the excess heat into the new heat storage. But they also know that if they build a big storage in their area, then all the other players will benefit from the investment. So they think that everyone should, the other players should contribute to the investment. Then, when faced with that, the other players say that we don't know what we're going to get out of it, so we don't want to just pay whatever. We need to know what we get out of it. So that was the problem that we looked at in our thesis and on the paper. We wanted to figure out what kind of different expectations do the stakeholders have for the storage. We wanted to figure out who will receive which benefits, and then we proposed some investment strategies and how to split the investment for the stakeholders. And this is just the different stakeholders that we identified: district heating companies, Ørsted, and waste incineration plants, and so on. So the approach was to partly do interviews to figure out how the stakeholders value a new thermal energy storage, what kind of expectations they have, and how willing they are to invest in this new infrastructure. And to sort of complement that, we had a modeling approach where we modeled the district heating system of Copenhagen and figured out how the storage would actually work within the system. And then based on this, we made this business model. And the first part of our findings was something about from our interviews. And we figured out that there were a lot of different expectations about this thermal energy storage. For example, the district heating company of Høje Taastrup, they expected that this new storage would be able to use the excess heat from their heat pump. That was what their idea about this investment was all about. But then, on the other hand, Cofor, which is a heating company in Copenhagen, quite a big player, they said that it would make no sense for the storage to actually utilize the heat pump directly. It should be a transmission system storage only. So there are two conflicting interests or ideas. Furthermore, we have Kano Wing, which is a waste incineration plant, saying that, oh, it would be great if you have a new storage, because then it would work as a seasonal storage, and we would be able to produce more heat during the summer where the demand is very low. But opposed to that, we have WEX, which is a transmission company, saying that this would most likely be weekly storage with weekly cycles. And some other things, Hofor expected that the CHP plants would earn more on the electricity market, and VIX, they expected that the heating companies would get a lower heating price. So there are a lot of ideas about the storage, but the final conclusion was that all these actors, they in order to make the investment, they wanted to have an idea about how it would actually work, and that would be based on some calculation and modeling. Following this, we decided to make our own model to test some of these expectations and assumptions about the storage. And in order to do this, we used Energy Pro, as it has the ability to model sort of local systems as opposed to Energy Plan, which is more on a larger scale. We did it by testing 3 scenarios: a reference scenario without thermal energy storage, and then 2 alternatives with 100,000 cubic meter thermal energy storage in White Cluster, which was the project that they had proposed. And in alternative 1, we only tested the heat pump supplying the distribution system of White Cluster, and the other alternative was that transmission system. So the heat comes from the transmission system in the heat storage and back again into the transmission system to be supplied across the whole of Copenhagen. And a little bit about the model. We modeled all of the different areas in the Copenhagen system with all the bottlenecks of the pipes in the system. And within every system, we modeled every plant that's in the system and all of their different units. For example, Ørebakken, which has several units, we modeled them all. And based on this, we had a full model of the Copenhagen distribution system. And to go to our findings, we confirmed some of the actors' expectations that the new storage will actually decrease the natural gas production of the peak load boilers, especially in alternative 2, which was the one that we found was the better one. You can see that the storage would decrease natural gas production by about 35 gigawatt hours, which we saw as a good thing and confirming the expectations. And regarding how the storage would work, we can see that it would be more of a weekly cycle storage than a seasonal storage, as you can see that it will be charged and discharged all the time, maybe about 50 times a year. More so in the second alternative as well, confirming that it should be a transmission system storage. We also looked into where the different savings come from and which stakeholder would actually get what kind of benefit. And we could see that on the income side, the electricity sales would increase from the CHP plants, and the expenses from fuel costs will also increase due to more production on CHP plants, but the expenses for operations, maintenance, and taxation of natural gas would decrease, leaving total systems savings of around 6 million a year. And these 6 millions were then split across the different stakeholders of the system. So these names maybe make no real sense to you if you don't know the system, but these are CHP plants, all these, yeah, these four are CHP plants, and these three are waste incineration plants, and these are the transmission companies. And we can see that depending on which scenarios we pick, the benefits would vary a lot. And in alternative two, which seemed to be the best option, most actors in the system would increase their incomes, except from ARC, which is the new waste incineration plant, which would actually have a lot lower incomes. So summing up, there is a general shift from natural gas to biomass, and the CHP plants will produce more and earn more incomes on the electricity market. Most actors would benefit from thermal energy storage, except for one. And all of these considerations were what the stakeholders were asking for the business model, because how would they put down the money for the investment if they don't know how much they will receive? So this is an indication of what they will actually receive. And so based on this, we proposed some business models, and the most obvious one or ideal one would be to base it on marginal costs. Like if you had a battery on the electricity market, you could buy electricity when it's cheap and sell it when it's expensive. And the same way in the heating market, it would be nice if a stakeholder who owns the thermal storage buys heat from the transmission grid when it's cheap and sells it again when the heat is more expensive, following the supply and demand. But in the Copenhagen district heating system, this isn't possible due to the current market structure. Because in the market in Copenhagen, the heating price is the same throughout the year, but the different plants are scheduled based on marginal costs. So it's sort of reverse market structure. So this would make no sense because the heat only has one price. So that idea didn't work. Then we proposed to just split the calculations based on, let's split the investment based on some calculations that we did, and individual players pay according to their benefits. But then we have this general idea from some of the stakeholders, especially before, who mentioned that different businesses or business actors, they can't invest together because of conflicting commercial interests. So this idea didn't work. And then we had the idea that producers could pay through a common tariff by reducing the heat costs that they take for producing the heat. So by using the storage that the heat companies invest in, the producers could give a lower price of the heat. But if you do it common tariff, then some stakeholders would be more happy than others because they receive more benefits than the others. So we had to split the bill based on individual tariffs, where stakeholders who earn more from the storage, they need to pay more, and vice versa. However, the general reaction to this was that it was too complicated, because then new contracts would have to be negotiated for each and every stakeholder. And to do that, it would take too much time and effort, and it wouldn't be worth it. So that's where our thesis ended. Like we had all these ideas, but none of them seemed to work because of the complexity of the system. Now we have almost a year later, they still haven't made the storage or agreed on it, but they decided that the investment will be made this month, or they expect that it will be made this month, and it will be a general agreement based on a Balmoral model, which VEX has, and then VEX, which is a transmission company who presumably will be the owner of the storage, they go out to each and every heating producer and say, do you agree with the parameters that we put into our model, and do you think we should change something in order to make it reflect your benefits? And then based on such a round, they come to an agreement, and they will make the investment. Because everyone can see that it does make sense, even though we don't know exactly who's going to get what. And they decided that there will be no post-investment calculation of how much reactor actually got. They will base the investment on modeling, and then it will be out of their minds. They will just keep going as. And this idea about making investment decisions based on not knowing, that's sort of what the idea of the paper is, to look at how you can coordinate investments in non-defined technologies that we don't know exactly how they will work in a multi-stakeholder environment where we have a lot of interests, and in a market architecture that's not just the free market, but it has certain rules that you're bound to follow. So in the paper, we'll most likely take a sort of valuation approach as opposed to the modeling approach to describe these different valuations and expectations of the different actors and how they agree on the business model. So that was what we did and what we're currently trying to make into a paper.
Okay, thank you. Okay. Are there any questions? We have like 6 minutes. So.
Yeah.
Could you go back to the slide where you showed the different benefits for different actors? Because is it correct that there are 2 different waste incineration plants, and one of them would have the benefit from the storage, the other not?
Yeah.
How can this be possible? It's the same technology. What is the reason for
it was due to bottlenecks in the system.
Okay.
So there is one crucial bottleneck in the system. As you can see, there's only one pipeline that connects CEPR from VEX, and ARC is in this area. We have a lot of CHP plants, while the other 2 are in the other area, and that has an influence on who will get more.
And what is the opinion from ARC on the final decision?
Sadly, we haven't. We didn't get an interview with them.
Okay. And the other question I would have: can you somehow describe a certain lifetime or service time to the pit storage until like significant retrofits have to be made?
I think we assumed a 30-year lifetime,
okay,
which was sort of the technology data that we found, and it's just a hole in the ground with the water, so it's not a lot of maintenance.
Okay. And then, apart from this the pit thermal storage project, are there also other like scenarios to install heat pumps or something like this in the district heating system?
There are the different companies have different ideas. We only tested the storage in our park, but all of the different companies have different ideas, and I think one of the most crucial barriers is finding space for both heat pumps and thermal storages, because it's so densely built that in the central Copenhagen area there's not a free ground where you can just dig a hole with the water in. It would be too expensive, because there's apartments to be built and money to be earned that way.
Because actually I was just wondering, because I think changes in the supply system of the heat supply, such as installing heat pumps, would again significantly influence and probably also affect the distribution of the benefits of the storage.
Yes, probably. And you say that this was our model, and there are a lot of assumptions going into our model, and the electricity price plays an important role in that. So other models, the different companies have their own models as well to test if they agree with each other. So.
How fast is the model?
It
Looks a bit complicated.
It got faster and faster as we made it more.
Okay, but does it take like?
I don't remember the exact running time, but I think we got it down to like 5 or 6 minutes.
Okay.
Yeah. But at one point we had it up at hours. We had to clean it up a bit.
Okay.
And there are also some simplifications in the different plants. Yeah, so we have made some edits to each unit to make it more to simplify it a little bit.
Yeah. I think isn't there a group working within it before?
Yeah.
Yeah.
Yeah,
So maybe this is good inspiration for how you could do your system.
our system is really smart.
Okay. Are there any other questions? Anyone looking back? Yeah.
You mentioned the different operation types for the stores, and what is transmission system storage only? I think it,
So the transmission system is the like in electricity vocabulary, it's the large pipes that go across the whole system. Those are up at around 90 or 100 degrees. And then in every district heating area, each municipality has their own system with their own temperatures. And that's the difference between transmission and distribution. And what we then did with the storage was that to test if it should be high temperature storage on transmission system, or it could be a bit lower to only fit the distribution system of high cluster. And that's actually what we have here. We just tested. This is high cluster, and the storage is in here, and we just changed the qualities of this link, saying that in this picture it only delivers to from the transmission system to high cluster, not the other way around, as you can see on the arrows. And then on the other alternative, we put it both ways. That makes sense. Yeah.
Okay, I think if there are more questions, we take them in the break after the next presentation. So thank you. Did you send the presentation?
Yeah.
Can you see? I have it on.
Yeah.
So, I'm Salvatore. I'm a PhD student at Napoli University of Napoli in southern Italy, and I'm a visiting PhD student in Hamburg University. So, I'm going to present something about the strategy and action towards the achievements of the European targets in the southern Mediterranean area. And in particular, I want to present to you a smart renewable energy system for a company region, and the strategy and action toward the achievements of 2030 European targets. So, an overview of the work, I will present a European and energy national strategy, the company region, like geographical information, and all about you have to know about the region. The methodology and tools that I have utilized, my group research, because this is a group research work. And the results, the conclusion, and the future works. So these are the European targets that are now settled, and in particular, the 2020 strategy with the increasing of the renewable energy use of the 20%, the less percent emissions of with respect to 1990 of the greenhouse emission, and the efficiency, the increasing of the efficiency of the 20% in 2020. Instead, for 2030, the European Commission stated that we have to have the 27% of the increasing of the energy efficiency and 40% of decreasing of the greenhouse emission, and the 27% of the efficiency of the technology that we use. And for 2050, we have to reach this objective, that is the reduction of 80–90% of the greenhouse emission. In particular, for the water consumption Italy, we have to reach this target of 17% of the renewable energy use and the 13 decrease of the CO2 emission with respect to 1990. And in Campania region, we have to reach this objective because we have a sort of burden sharing in Italy that we have to respect, and in particular, not we have not the same objective to reach with for each region. And so this is the objective to reach in 2020 for Campania region. And I want to say to you that we are not in the renewable energy use in Campania region, we have already reached just now the objective, and we are at about 16% of the renewable energy use. But we have to do something about the greenhouse emissions and about even the energy efficiency of the plants. And so the aim of the work is to create a specific strategy in order to achieve the 2030 European targets in Campania region. And according to the aim of this work is to design a scenario of transition, because 2030 is a transition scenario towards the 2050 scenario. And so we want to reach these two objectives. The 40% of the reduction of the greenhouse emissions and the increasing of the renewable energy use. So these are the features of the Campania region. You know that I want to underline that we have two, this is the Napoli city, and we have two volcano regions. We have Vesuvius, that is very, very known, but we have another very, very big volcano that is called the Campi Flegrei. So we have the availability of a geothermal resource, but we never use this resource because of some problem with the people that can't accept, because they are very afraid of earthquake that can generate the use of a geothermal resource. And the geography is characterized by hills, mountains, and plains. So we have even hydroelectric energy in in Campania region. But I want to underline this one, this characteristic. We are in Italy different climate zone, and in particular we have a climate zone that is called C, D, and E in Campania region. C is with high temperature in the weather, and the 82% of the population are concentrated in this area. So where the climate is it's more warm than the other region. And this is the characteristic of the population of only the region, of Campania region. You have to take in account that the territory is 15,000 kilometers square, and this is the population of the Campania region. If you consider that, for example, Denmark, it's I remember 43,000 kilometers square, and the population is quite the same. You can imagine that there are a lot of people in a single zone, and in particular in the region around Napoli. This makes a net density of the demand. And so even for district heating, it's a very convenient to have a district heating strategy and even cooling. So this is the sample diagram of the energy of Campania region. I want to underline that we have the for water concerns, the heat demand is supplied, but it is supplied by natural gas overall, and even another thing that I want to underline that the transport sector, heat demand and electricity demand are not matching each other. So this makes this system not smart. So yeah, even for electricity and the transport sector are not matched, but even heat demand and electric demand are not matched, but only with this part. So we have gas, natural fired power plants, and in particular that give electricity to the system. So we have in Campania region thermal power plants, but they give only electricity. So we have not combined the heat and power plants. So this new strategy for Campania region, we have the energy. We have divided into 3 parts. So we have the collection of the data, the analysis of the system, then we have the measure to implement, and then we have the future scenario to create. Particularly, we have to underline that energy production demand, we have followed a particular strategy that then I show you. And this is the energy sources, renewable and fossil energy. Yeah. And this is the key factors. This is climate and geography, the population growth, and the policy activity. So after a data collection, we have an analysis. So we have chosen a optimization criteria, and in particular, we have chosen the optimization about CO2 and the renewable energy use and cost analysis even. And then we have a strategy energy change that we have to implement, and then we have the software that we have utilized to have these to create this scenario. The measure to implement. When we reach the goal, we have reached the new smart energy system. So these are the 2 tools that I have utilized to have to obtain the transition scenario of the Campania region. And in particular, I want to underline that I have even used Transis software. Transis 17, it's a software that give the possibility to simulate each technology that you want to install. In particular, then you can obtain the production curve of the single technology that you want to start. So even wind, solar, and solar panel, and PV. And this gives you the opportunity to have the results in the single zone that you want to install the technology. I mean that if you want to install in the northern part of Italy, you have a weather file to simulate the production of the PV plants, and even if you want to simulate in the southern part of Italy, it's different, and you have another weather file, and you can simulate differently, and the production are different. because the irradiation is different. And I have utilized, of course, energy plan software to simulate the strategy, and in particular, cooling demand and the cooling, the district heating and cooling, and even the CHP plants. And then I show you the numerical model that I have utilized to obtain the thermal demand and the cooling demand. And in particular, I have utilized it for each climate zone that I have in Campania region, and I have made even an average on the population that live in this area. And then I have set the temperature of the plants at 16 degrees, so they stop at 16 degrees. And I have even the hourly outdoor air temperature, and I can obtain this curve. And I will do the same for the cooling demand, so taking in account the different climate zone of the region, of the Campania region. And then I have made an average of the population that live in this zone. So obtaining a more realistic result about the cooling demand and the thermal demand of the region. For what concerns instead the PV production, I will utilize, as I said to you before, the Francis software, Francis 17. I have installed the capacity for each climate zone, and I can obtain the curve production. And here I will do the same even for solar thermal panels, but for this technology, I have found another software that is used in my research group, that is Design Builder software. And I have simulated a gross area collector of 4.4 meters square, a tank of 2,000 liters, and daily consumption of 1.0505 liter per meter square, and a typical flat of 110 meters square. So I have done a calibration of the reference of the model. So I have a reference model by 2014, and these are the wind production estimated by the current data, and the energy simulation and the energy plant simulation. So we have a little, so not so much different. So the calibration of the one model works not so bad, and we have made even a comparison between the CO2 emission. These are in the pair. These are the measured data, and these are the energy plan from energy plan. And we have done the same with the renewable energy electricity produced, and the rest share of S. So this is the designing and forecasting of the energy demand by 2030. So we have for the electric demand, we have an increase of 1% per year. So we have an increase of the electricity demand for 2030. For what concerns instead the residential demand, we have shifted from individually heating to district heating. So we have shifted a part of the demand in the district heating strategy, and we have even make a energy saving of the heat demand. So we have a decreasing of this residential heat demand. We have even for what concerns the electricity cooling demand, we have estimated that we have an increasing of the 70% of the cooling demand at 2030, but we have shifted part of this on the district heating cooling demand. For what concerns the industry, it's quite the same. And for what concerns still the fossil fuel transport, we have a decreasing because we have an improving of the energy, of the efficiency of the engine of the cars, a little slow, a little decrease, but we have even a shift of the electricity from the fossil fuel transport to the electricity transport demand. So we have a diversification of the technology and integration of resources with respect to the 2015 scenario. This is how we obtained the geothermal district heating and cooling, the feasibility. So we have we can note that in this area there is a high density demand of thermal demand in this area, and so we can say that even the economic feasibility of district heating strategy is quite profitable. It is profitable. And we have to say another thing, that this area where we have a lot of people living in is the area where we have geothermal, the geothermal production, the geothermal resource. And so this makes the amount of energy, the geothermal amount of energy, highly profitable. So because it's concentrated properly when where there is a large amount of population living. So these are the biomass resource. I want to skip on this because I want to say to you that now we in Campania region we have power plants supplied by gas, natural gas, but we want to shift this two-thirds of this in biomass and one-third in natural gas too. And we have the amount of energy of biomass resource in the Campania region, and we have make a comparison between the needs of the power plants and the resource that we need that we have in the region. This is the electric vehicles, and we have two scenarios that we have simulated, but I want to underline that we have this one, with the 14% of the electric vehicles to 2030, because it's more realistic. This is the increasing of electricity by RES, and I want to underline that this is the amount of wind that now we have in Campania region. This is, and this is the increasing capacity that we can have. In particular, for what concerns wind energy, we have a lot of constraints in Campania region because of the landscape and because of even offshore wind it's quite complicated to have because of the landscape that we have, and we have a lot of island outside the coast, and even the level of the sea is very deep, so we have to consider it's very complicated to have. So the smart energy system that we have thought is composed by solar thermal, geothermal heat pumps, feed by geothermal energy, absorption heat pumps, feed by geothermal energy, biomass, and the natural gas CEPR plants that feed the district heating network, where then the smarter grid, the PV panels, thermodynamic solar panels, wind, hydro, and biomass natural gas CEPR plants for the smart grids. These are the results. We have created different scenarios, geothermal, biomass, electric vehicles, with increasing of RES electricity by renewable energy source and increasing of the waste energy use. And we have found that we can reach the objective of 2030, so with about 27% of the RES of share of gas, and the reduction of 40% of the CO2 emission. I want to underline that this import that we can see here is due to the electric cars that we have put into the energy system. So we have an increase of the electricity import in the system due to the electric cars. These are the final results for the general energy consumption, and we have a decrease of the 70% of the primary energy supply, and we have the increase of the geothermal energy use, the decrease of the oil consumption. These are the results of the cost analysis, but I want to show you the results because I think I am a little late. These are the unit energy price for thermal energy and electric energy, and this is made by geothermal pumps, absorption heat pumps, and solar thermal for what concerns district heating network, And the solar, the smart grid composed by this kind of technology, and the price are comparable with the current prices that we have now in Italy. The conclusion is that in analysis, I want to only to underline that the price to the corresponding scenario by 2030 is comparable with the current energy price and probably less than the future energy price if we consider literature forecasting of the fossil fuel price. And I want even to underline that the construction of the district heating cooling system has been evaluated from an energy and economic point of view, resulting in a feasible and a resilient solution. We have even done another work in Italy with a district heating and cooling network in a little city, so we have some data about this. So we have evaluated even taking into account another work. For the field work, we want to have an economic analysis taking into account the different forecasting for fossil fuel price and technology, because the fossil fuel prices are not you can forecast, but it depends on the economic situation of Europe, of the world. So you have to make different forecasting, high, low, and medium price. And we want to do a different optimization criteria. And even we want to make a detailed analysis on the region of district heating and cooling that we are supposing to realize. So this is another work that I want to present, but I think I have not so much. Okay.
Yeah. Thank you. So we have 7 minutes for questions.
Yeah.
You spoke so fast. So there are a lot of questions. So you can point at, just point at a person, and then they will ask.
Yeah. So, you're...
Okay. Yeah, I have a question regarding geothermal, because I see there's a huge potential in this region.
Yeah.
But I wonder if, for instance, the district heating company decides to implement geothermal heat pumps, could they just buy land close to the volcano? Who owns this land actually? What kind of planning procedure is needed for the district heating company to install a solution?
There are private land.
Okay, it's private.
It's private. It's most of them are private, but there are different situations. We have in particular one example that a private has got the land, and the government tried to buy it,
Okay.
but then the procedure failed because they asked more money, and so it was not feasible to buy the land.
Okay.
So it's very complicated. We have 1 or 2 experience, and 1/3 it's a failure. Okay. And in Italy, we have not, we have here other experience of geothermal district heating, and it's in Tuscany, and it works very well. But in particular, in our zone, that is Vulcan, present even at the Vulcan, and not only geothermal energy, it's different. There are stakeholders and even people in general are afraid about any well that you can do in the land. Yeah.
Are there some political barriers that might complicate the implementation of these ideas?
Political barriers? No. Now in Italy we haven't got a government, so I cannot just now. So it's difficult. It's very complicated to answer your question. But the last government, they give a lot of policy, something that we can give you help to realize this kind of project. So with the last government, there was the sensation that it can be quite easy to realize this project, this kind of project.
And the local mainly local authorities, they support these things?
Yeah, the local authorities support it, especially university. But for what concerns but even the municipalities of the zone. I have talked. I have some meeting with the measures of the cities, and all of them, from my experience, they were good.
You mentioned in the beginning and also for the minute that people are against the geothermal energy source because they're afraid of it somehow. So do you have, yeah. So do you have some kind of strategy how to convince them?
No, the only strategy that we have is to talk with them. But we have, in Italy there is a very big problem that they don't trust the authorities. They are not so. They scared about them. They are not so, and so you have to talk a lot. You have to do a lot of meeting, presentation of the project. You have to have the precise results, the number that you can give to them to be more credible. But for what concerns other policy that we can't have, I don't have any idea, but probably in Italy someone has. It's only my opinion.
Okay, I also have a question.
Yeah.
Do you, maybe you said it, but do you already have the district heating or do you have to build it?
No, I don't have a district heating.
Yeah, I don't.
Yeah.
Okay, so there's no district heating or cooling.
But you have district heating in Italy only in the northern part of Italy, because the heating demand is higher, of course. And I show you how it's composed the heat in Italy. So it's like this. So we have three zones. This is the climatic zone. And northern part of Italy, it's there is a high density, high thermal demand.
Okay.
And in southern Italy, instead, when you have a lower heat demand, the district heating it's not so feasible. But if you mix with the cooling demand, this is we have made a study that is feasible from an economic point of view. That's why we have considered district heat in the heating cooling strategy and not only heating. Okay.
Okay. I have final question. It's more the modeling you do. You use like both trances and energy plan.
Yeah.
So what are the benefits of using energy plan?
The benefits, it's for us that in Italy we have not measured data from the company. For example, wind. Yeah, you have to simulate the production of the plants, or the wind plants, and so sometimes we have to simulate with trances because we have not measured data. And it's the same for PV plants, and sometimes even with the solar panel. Yeah.
Okay.
And with this, it's the only way that we can have a more realistic results.
Yeah.
Because with transit software, we can even change the technology. That you even for PV plants there are different technology that you can use, and you can make a very high resolution in this sense.
Okay, and then you cannot model the whole system in trances, or why do you use energy plan then?
No, I cannot model the whole. It's very, very complicated. We have done a district heating and cooling model, but only for a city, and it was not a large city.
Okay.
And if you want, because you have to model even the strategy, you can model even the strategy, and so the controller on the action, for example, of when you give the temperature to the system. But if you want to model a whole region, it's impossible to make. Okay. And that's why we need the energy. Okay, that's a good reason. Yeah, it's impossible. Okay, I think we'll take like 10 minutes break. So 20 minutes to 2, we'll start again and have Jacob's presentation.
Also, Yes, as you might know, my name is Jacob, or Jakob, if you want to say it. Proper Danish. Anyway, I'm an assistant professor here now, and I will present a new tool we are working on for energy plan. In other words, meaning that it's not at all done, available yet. But Søren took my topic, so I have to something else to talk about. And on the other hand, I also think this could be interesting for you because we assume it will be done, or at least work will go around right after summer. So if it's something you want to do on later semester, then you could maybe use it. Anyway, so why are we doing it? Actually, I want to go to this later. So the reason why we're doing it is we're looking more and more into what does system interconnection, so interconnection between countries, mean for smart energy systems. So when we do heat pumps, and gas and thermal storages and all these things, well, we're also competing against just transmitting that electricity to some other country. So how can these things actually balance? An energy plan is not necessarily very suited for making that analysis. You can say it's very suited for doing the energy system integration, you can call it, but it's not necessarily very suited for doing all of Europe or whatever geographical framework you have. And the reason why it's not necessarily suited for doing that is that everything is the same size in energy planning, the same from a geographical point of view. It basically takes all of Europe and then just squeezes it into some spot where the whole energy system is on top of each other, basically only with the you can say separation between different district heating grids. So whether it's Germany or Denmark or Europe or Copenhagen or Nykøbing Mors or whatever it is, it's basically the same parameters you're working with, meaning that when we start wanting to model something like this, where we have a lot of interconnection between different parts of the system, we cannot really capture the limitations on the transmission system. So are there any bottlenecks? We cannot really capture if wind in this is good to send to here or something like that and what that would take. And if that's a better solution than just using a heat pump. Like all these things become more difficult to do if you're just using energy plan right now, because it's a single energy system. However, it has the advantages of having the entire energy system doing hourly simulation, meaning that we in every hour could potentially figure out what if we can in energy plan figure out, well, can we transmit something, and we have an external market we can work against, but we cannot really necessarily model that external market and other things than just the price. We can either find somewhere, the price has already been set like today, but if we model in 2050, what is the external price anyway? Can we predict that? Is that interesting? So instead we're trying to do something totally new. But first I want to talk about what we have done so far. That is not new. And why this is not the solution we're looking for. Star Wars reference. Anyway, we have multi-node right now. I don't know if any of you have seen it or used it. But this basically only takes the technical simulation of energy plan and uses for transmission. So it has a very set way of thinking, meaning it runs all your systems you might want to interconnect. So this could be Denmark, Germany, Sweden, for instance, and say in all these hours, if they run in island mode, when could we potentially, when are we overproducing? So when do we have critical excess? Or when are we not producing enough? So do we have an import demand? Or are we producing on a power plant we don't want to run? Then it figures out on a common grid between these three systems, can some export from Denmark fit with a power plant operating in Germany, and then they will do an import-export balance between them, saying, yes, that fits. We move some electricity from Denmark to Germany. We recalculate and see that that's a good or better solution. And yes, this will give you a technical understanding, but it won't really make a power plant compete with another power plant in another country. So if I have a very, very efficient combined cycle gas turbine that runs only when there's heat demand, so the electricity price is basically zero, you could say. I don't know if that would technically make any sense. But and then in the other country, in Poland, they still have, in Germany, they have very old, not so good coal power plants or something like that. We might want to make that transmission as well. Or what if we have a very cheap storage available in another country? Marginally, could we then run something there? The second thing is this doesn't take into account the operation cost, because this is basically just based on we want as much variable renewable energy to replace fossil fuels or power plants. So that's one of the reasons why. So this is based on a more flexible priority, you can say, where we use the marginal production price to prioritize prices instead. At least that's the idea. I'll come into how well it works right now later on. The second issue is that multi-node combines all the systems into one grid, meaning that it won't capture a bottleneck. So let me just illustrate. So if I want to send electricity from system 4 and system 1 to system 5, well, I might have 1500 of megawatts here, but I only have 1200 here. Does that make sense? So, but if I go over here and I say, well, system 1, oh, sorry, that has a total of 1800, because that's, it has even, oh yeah, 1800 here, and system 5 has 1500. That's fine. That means I can easily send to 1500. But if this was the actual layout of the grid, and not, then it won't capture the bottleneck. So that's another issue, that if you use very distributed systems, like if you go to other places in Europe and there's like on different places, then this works well as a generalization if it's a very well integrated system. So if it's within a country, you're dividing it into different regions, like Denmark so far. If you take Western Denmark and someone wants to model that as 3 different, well, this assumption might work fine. But if you want to start sending energy from Denmark to Turkey or something like that, then you might encounter bottlenecks you want to include as well. So that's the second issue why we want to do anything, because when this was developed, the multi-node tool, it was developed within urban to countrywide scale. So we were saying, how well does a city fit in a region in Denmark or something like that, or within Denmark, where now we are wondering more towards, well, what happens to the whole of Europe when we do different things in smart energy system perspective. So that's the second reason why. So what are we doing? We're basing it on the market simulation. And some of the next slides I will not be able to answer questions very well to, because that is something we do in almost. Yeah, I have hand drawings in my slides, but this was the best representation I have anyway right now. So what we are trying to do is we in every country figure out, and we model the different market prices based on the operational cost of the plants and energy plants. So if you go to the variable O&M cost slide in the energy plant, it tells you this is when you turn on a CHP plant and you don't turn on a boiler. This is the price for turning on a power plant. So at all these different prices, how will the energy system operate? And then the idea is that for every hour we get a price per megawatt hour, marginal price, and we get how much import or export does that account for. So we create an import-export balance, meaning, okay, if the price on the market is 55 Danish kroner per megawatt hour, that's very cheap, actually. But if that's the price, are we then importing or exporting? Like, how are our production plants? Are we relying on a cable, or are we producing on a power plant ourselves? And then we do that for every price, so we in total can generate these cost curves, you can say. And then we do that ideally for different countries that are interconnected in all the hours and based. So that is what energy plan does basically. So it creates a lot of 8,784 curves of around 30 points, you can say. So there's a lot of curves like this being split out. And then it goes into a model developed by Aarhus University that actually does network balancing. So based on these inputs here, so it defines all the intersections between them. So at the intersection, it finds out, well, what is the price where this cable will either import or export over these space. So what happens is that you, with the new tool, you develop each of these points, you can say, are the energy plan models. Within the tool, you then define the transmission capacity. The energy plan model outputs and the transmission restrictions are then fed into this Aarhus model and then balances the grid based on these constraints to create the lowest total price, or total lowest marginal cost price for the whole system. That's basically what it does, and it might be a little bit confusing. But the reason why we are again doing it is that we can do the sector coupling. Why we're not just doing energy plan? The other thing is that we can do sector coupling, hourly simulation, and the full energy system. In energy plan, the representation currently of interconnection is not necessarily the best. The good thing about power flow is that it doesn't favor anything you can say in terms of Denmark is better than Germany or something like that. This has to be the first one. It's basically based on whatever parameter we could give them. So in the long run, we also want to be able to do other things to maybe margin prices. We could give them coal or CO2. We just need to give some kind of a function that it minimizes. We can also expand it to do a gas grid if that's what we want. The reason why we're not just using power flow is that there's no sector coupling. That means it cannot really take into account district heating or storages across sectors and stuff like that. So we need energy plan to be able at least to say, well, at this price, it's very good to fill up a storage in this country. And then the other countries say, well, that's fine, that we can use power flow to make sure that we get some electricity from another sent to that country to fill up the storage or something like that. And then that's it doesn't really model dispatchable plants. Basically, power flow right now only operates, or when also running it alone, and basically you just have wind and solar, or whatever variable renewable energy you're putting in, and then it could curtail that, or it could reduce the risk of something. It could be about the risk of the electricity that is needed, so it has to balance the grid. So it couldn't really take into account different types of plants. So we have made a website because that's the second thing. This will be web-based interface, whatever it's called. Meaning we have, as a user, you define your energy plan scenario, so you have to make those yourselves or find them somewhere for an energy plan, and you define the transmission lines and capacities. Then you upload them to this website. I'll just show you in a minute. Within there, the website currently runs the energy plan for each scenario, create the marginal cost curves, run power flow. So the blue is what it does so far. We are still to actually put out a new energy plan file for you as a user because we are not quite certain exactly. We're trying to figure out what output makes more sense to put into the model. Whether we should. The idea is to put in so the power flow runs, and then it gives you an optimized. Really gives you the market price for Austria, for instance, that you can then input into the external power price market in energy plan. But it can be other things as well. Let's see if this works. Can you click a website? And we'll probably get it over here somehow. So this is how it looks like. Basically, you have it's very, very simple. You drop some files in here. If it's a .text file, it would be the scenarios. This is Austria, Czech Republic, Germany, France, Netherlands, and Poland. And the zip files is the distribution. So if it gets a zip file, this is why I wanted to get Peter's tool, because then you can create very easily. You can create these easier. You can create a zip file with all the distributions needed. I have a problem right now basically uploading my whole distribution folder every time, and that's quite big. If you've ever been to the distribution folder in energy plan, that's very, very messy. So I wanted to clean it up and stuff like that. Anyway, you drop those files, just recognize it as zip, this, and then you define the capacities between them. So if it's 2,000, do that, or whatever. And then, so if there's no number, it's infinite, that means you have all the capacity you want. So if you don't want any capacity, remember to put in a 0. And then this is where it gets tricky because I don't think it's working right now. But if I press submit, yeah, then this, and then it will email me the results. But the problem is right now, I think I broke it by putting up this distribution folder. So we are still testing it, and we got this to work 2 weeks ago. So still very much in progress. The reason why I need a password and email or username is because right now we're using it. There's some licensing issues on the end of the Aarhus tool in terms of the solver they use, mathematical solvers. But since you're all at the university, you will easily can give you username as well, because you will use it for academic issues. And that will probably have an expiration date at some point when you're done at the university. Or we'll find a free solver. I think that's ideally what we do. So some results, just finally to remove this out. But I don't know how exciting these results are because, to be honest, I realized an hour before I got here that something had happened with my files. So you can say that this might not be the actual results that will come out. But basically, I've just compared what actually happens in the system on the fuel point of view. This is from Czech Republic, Czechia, and the power flow will, in this case, start import a lot of energy instead of having it from itself in terms of the power plant, because it's cheaper. And the resulting is maybe more chaotic, but also what actually happens within, what is the result of what it does is to get all this activity on the transmission lines. So the greenish color is import and the blue is export. So it has a steady flow of import. So it seems like the prices given for Czech Republic with this tool means that there's a more efficient power plant available in some other system that it wants to basically take energy from all times. And then once in a while, there is an overproduction of renewable energy or something. They don't have a lot of renewable energy in the system. So in those cases, it will export that. Are you asking questions already, Carl? We can do that. Let's go to questions. It's also over 20 minutes now. Yeah, do it, Carl. That's more fun than me talking anyway.
Oh, sorry. Yeah. I didn't want to interrupt.
You can do it. I just have the same for Italy and then I'm done. So.
Okay, we'll finish it.
Yeah. No, but basically, and this is where something funny happened where it suddenly gives a marginal price of 8 quadrillion euros per megawatt hour, which is so. There's a lot of things you have to figure out this right now. That's why I don't want to spend so much time. And then you get something like this suddenly happen, which is basically, it seems like just an export going up and down, and then in the summer there comes a little bit of import. But this seems kind of odd, I think. So that's just to illustrate that it's not working. There we go. Fire away.
And it's just wondering why is it?
So the reason why we're doing it on the web page is then we well, there are two reasons. First of all, we wanted to test out if we can do these things instead, because it's a little bit more accessible if you want to give it, and especially because version control, you can say, so we can make sure that they have the right version of Energy Plan to make this run is on that server, and always make sure that the right version of PowerFlow with all the necessary tools, or it runs in Python, and if anybody uses Python, in many cases you have a lot of scripts or different things from outside that you have to have installed.
So it's easier to integrate these two different.
It's easier for the user because they don't have to make sure that the tool works on their computer. We make sure that they work. It's easier for us in the sense that we can work individually in Energy Plan, and we just need to make sure it works in here. We don't need to make sure it works on every individual computer. The second thing is you can use it on a Mac if you do it through this.
Finally, I can start using that.
But you just have to have a Windows computer to create the scenario files, of course.
But then I guess on the homepage you could also show some, some typical inputs for the European transmission line.
We want to make it more. We want to make it more. So this is the first step of it, but we want to do something like where you could, for instance, click. So you could basically do the map I showed you earlier. Click somewhere and say, this is my first node, and this is my second, and then you can kind of visually create the grid like that. That's also something, but
Very interesting.
depends on the time.
How do you how virtual or how real is this? Kilowatt hour from
that's a whole other discussion, I think. As far as I understand it, this is not what it's like from a very, very small, detailed frequency point of view and stuff like this. Then it's not really suited for. But for these overall transmissions, I think it's not. As long as the grids, of course, within the countries are also strong enough to do it, we could say that basically it will replace demand, you can say, potentially all the way down. Saying that the electron produced in Norway is the one that actually arrives in Turkey is probably not correct. But the way you could shift production types and stuff like that all the way through, you can say that it can influence. And that's what it models. Other questions? You get it?
So 2 questions. One, how much time did it take to run when it worked?
From my first start, and I have these results that I showed you were based on 14 countries and not just on 6. It takes 10 minutes.
Second one is how many countries can you have people in a mesh? Is there a limit to how many you can have?
As far as I know, there is not a limit. On calculation time, there probably is. I have not tested that, so I don't know exactly all. I can ask, but right now they assume on their end to do 30 countries like that would take 5 minutes and that's approximately the same time it would take for Energy Plan to calculate doing this way, and then there's no trick communication back and forth with the server. So 30 countries, all countries of Europe, in around 10-15 minutes. Then yeah, there can be difficulties and that's actually the biggest worry of having a web page right now for us is if something happens at the server, the user gets, like, I don't get any feedback right now if it just doesn't work. I can still wait forever. So that's the issue right now. I don't know if it's because it's just a long calculation, because all the you have to somehow deal with it. All the prices are basically on top of each other like this. How do you prioritize between those things? They have to have, and then that can create some issues. I really hope this was a lot of so these things could make the calculation take long. We don't really have a way right now of providing feedback to the user on these things. Stephen?
I was wondering, it's the market economic optimization in energy plan?
Yeah.
But how does it, like, if you have a heat pump, for example, in Denmark?
Yeah.
Does it then know if there then is a lot of excess electricity in Norway?
So basically,
does it then know that, like?
So the way we've sets up energy plan is that it assumes an infinite transmission capacity when it calculates this to begin with. So it says we have all electricity available in the world to us, and at this price, if this is the right price of running a heat pump, then it will do that, because then it will just import it at that price. Then when it comes to the second one, where it actually goes into power flow and the constraints and all these things, then that will influence whether it can actually then get all the electricity for that heat pump.
Okay.
So basically, if the price is right for the heat pump, then it would ideally import for the heat pump.
Okay, so it's kind of running everything at the same, instead of like the old model you showed.
Yeah.
You run all the models and then you determine if there's some excess somewhere. But this one runs everything.
You can say it
at the
runs
same
all the
time
model individually as well, but with the assumption now that all of them have fully interconnection between. So, for instance, if I take Denmark, then the first time, if I say I have Denmark, Sweden, and Norway right now, then it will run Denmark at the assumption that it's fully, like, with infinite cables to the outside world, and then at different prices, how would it operate? So if there's a price saying I want to run my heat pump as much as possible, then it does the same for Norway and Sweden. Then it with the Aarhus tool, it puts them into a grid with some constraints on and say, okay, so at this price, where's the cutoff for importing or exporting this?
Okay.
So it would have, like, saying, okay, there's only 2,000 megawatts, so we don't transmit this, and there's this amount of export going this way. And then the rest, and then you can feed that price back into energy plan with that transmission capacity. Then the energy plan will of course find what is the remainder, where should I get the rest of the energy production from now. So kind of a feasible.
Yeah.
I don't know if it makes any sense.
Kind of.
It's a little bit complicated when explaining it. You can also have your doubts sometimes when the energy plan is actually capable of doing this. That's Henry and I way.
And just consider about the storage part.
Yeah.
It can also take that into account. It doesn't sound like it, but it sounds like energy can delivers the basic things that you say for the power flow decisions.
Yeah.
And then only if there's a restriction somewhere in the system, you can be active. But how does power flow go with at an earlier time or something with storage?
So storage becomes an iterative process.
Okay, so there will be a feedback.
Yeah, so then there will be, if this, so that's step 3, and that I haven't shown you is that we need to see how it actually responds to storage. And also Henrik and I have to do a lot of work on it here in June about the margin prices, especially for storages. Because of small levels of storages, it doesn't really affect anything. But if you get Norway in that, something like that, then that becomes, the problem is that it has to calculate in more time to actually know, because the storage will affect the price afterwards. And to begin with, or the amount of electricity put into the storage will then affect the price, but you don't know how much you put in before, after you've done the calculation. So you do the calculation, then you fill up a storage, but then that has changed the whole price situation for that country. If there's a lot of storage, So then you have to do it again. However, I would say the Aarhus people assume this would take 2 months. Whether that's right or not, I don't know. We'll see. So if you do storage, it might take half an hour to 45 minutes.
Okay. There are no more questions, so thank you.
Thank you.
I think we will just stop, and then we have another one next week, and I can't remember who's presenting that. So, thank you.
Thank you.
Thank you.